we have many famous, unfortunately no longer living in many cases, scientists who were early users of Mathematica, whose actual sort of handwritten registration cards still exist. But I was just looking, was curious about, I don't know, something, and I was looking at the current batch of registration cards that just come in sometime in 1989. And I'd just been looking at, this was a time when Roger Penrose had just published a book called something like Emperor's New Mind or some such other thing, which was, and there was a summary of the book in Time magazine that then the summary was something like, you know, computers are all dummies, says Roger Penrose, or some such other, that's a paraphrase. And so I'd just been looking at this, and literally then I'm leafing through these registration cards, and there's a card from Roger Penrose. And it's like I was just really amused that the juxtaposition of the computers are all dummies report of his book and the, well, okay, they're not such dummies because this is a useful thing, Mathematica, that can be used there. I would say in the kind of famous users of things department, one thing we've been trying to track down, it's about to be the 20th anniversary next year of my big book, A New Kind of Science. And in sort of as one of the elements of that anniversary, we have been trying to track down sort of famous readers of that book. And one way to track that down is when there are pictures of people and you can see it on their bookshelf. It's an interesting sign. Now, the book happens to be, for those who've seen it, it's a very thick book, 1,280 pages long, and it has a very notable black and yellow spine. I'm sure there are ones up here. Yes, there's ones there. And so that's something that you can sort of readily see on somebody's bookshelf. And so we've been doing a little bit of a hunt on sort of notable people's bookshelves for, can you see an NKS book there? For example, there's a spotted on Bill Gates's bookshelf, spotted on Mark Zuckerberg's desk, spotted on an Elon Musk desk, spotted on various kinds of different people, different places where NKS books have shown up. But it's a particularly, it's kind of a problem not yet solved by image search and AI to go, you know, search the web for places where the book shows up as a sub piece of an image. But in any case, that's kind of an interesting sort of place to find out whether people have the book on their bookshelf. So if anybody knows of notable places where the NKS book is visible on a bookshelf or something, let us know, because we're trying to make a collection of these things. It's actually already a pretty big collection that we have, and I'm forgetting most of the places. There's some pretty interesting ones. The ones I mentioned, just a few that come to mind. So don't really know the answer to this most famous Mathematica users. It also depends on what you mean by most famous. Let's see, we have another question here from Alex. What separates the greats, by which he or she means Einstein, Dirac, Newton, etc., from everyone else? Is there a tip that I might have for a young physics undergraduate to become a better physicist? You know, a couple of comments here. I mean, it is usually the case that fields go through, and I've said this many times, fields go through these sudden moments of rapid expansion and growth, followed by 50 years, 100 years of sort of fairly slow growth. And typically what initiates one of those bursts of rapid growth is some methodological advance of some kind, or some new way of looking at or thinking about that kind of field, some kind of paradigm shifty type thing that's happened. And so what you'll typically see is a bunch of sort of notable discoveries clustered around the time when that methodological advance is possible. And in my own life, I've been fortunate enough to kind of be involved in a few things that I think have already turned out to be fairly important, and which I think will end up being vastly more important actually in the future. And in a sense, what I would say is that the main thing that's caused it to be possible to make those discoveries is simply that I've lived at the right time in history. And so, for example, back in the early 1980s, when I was discovering things by doing computer experiments on simple programs and so on, that was something that was readily doable in the 1980s because computer technology had reached the point where that was possible. And it would not have been readily doable if I, shift me back a few decades, that wouldn't have been readily possible. At some point, probably, those experiments get done. And so if you live sort of today, those most basic experiments have already been done. So it's kind of one thing is at what time in history do you live? Now, of course, there's a certain freedom because you know what time in history you're living at. And the question is, what's the thing that is just now becoming methodologically possible at that time in history? And of course, the other part of that story is that something for which you have some particular talent or skill or insight that you can bring together with the methodological advance that exists in the world to produce something that is sort of an exciting push forward. Now, if you look at, I think, well, let's take Dirac, for example, 1930s, involved in kind of the mathematicization of quantum mechanics. In a sense, what happened there was Dirac was a very mathematical thinking kind of person who was kind of brought himself into this area, quantum mechanics, that was this kind of new thing where, in a sense, it was both induced by some experiments, but also the result of kind of the addition of somewhat fancy mathematics to physics. In a sense, the development of physics, for a long time, it had been like, well, Newton kind of introduced the idea of let's use calculus to do physics, and that kind of developed through the 1700s and 1800s, Laplace, and then eventually Maxwell, people like that, into, it's a big differential equations festival, so to speak. As quantum mechanics came on the scene, there were things like matrices, which were an exotic mathematical concept at the time, and things about, all sorts of Hilbert spaces, all sorts of mathematicization that was sort of wheeling in advanced mathematics that hadn't been present in physics. Dirac was aware of that advanced mathematics and was able to combine it with this kind of interest in quantum mechanics that had developed at that time. And so he was kind of on the leading edge of the mathematicization of quantum mechanics and was able to make big contributions there. I mean, for example, the appearance of quantum mechanics at the time it did, I was thinking about this recently and trying to understand what was the kind of thing that caused quantum mechanics to arise 1900, 1905 to 1920s. I mean, basically the history is, Max Planck around 1900 realized that he kind of did this fit to the black body spectrum, the spectrum of electromagnetic radiation produced by just a hot object of a certain temperature, and realized that, you could get a better fit if you assumed that photons didn't obey the statistics that people thought ordinary molecules and things obeyed, but obeyed a different kind of statistics. And that was the Planck distribution, eventually Bose-Einstein distribution function. That was, he kind of realized as the sort of numerical fit to data that it could be explained if there was discreteness in photons. And then Einstein came along in 1905 and noticed that the photoelectric effect could be explained by the idea of sort of particle-like photons and so on. And then in the 1920s, there was kind of somewhat driven by things like the study of spectral lines and so on. It was kind of the introduction by Schrödinger of his wave equation, Heisenberg, his matrix mechanics, things like that. Those were the theoretical things, but there was an important, I think, experimental thing that happened, which was, I think, that quantum mechanics was the result of the invention of amplifiers. See, in the past, for example, a lot of development in biology from the 1600s on was the result of microscopes, the existence of microscopes, and you could see what were those organelles inside a cell. the development of astronomy, obviously, in the beginning of the 1600s, the discovery of the telescope, invention of the telescope, and used by Galileo in 1608 to find the moons of Jupiter. That was kind of a key moment in the history of astronomy. So again, it's kind of the telescope, the microscope were things which allowed one to see things that hadn't been seeable before and led to advances in fields of biology and astronomy and therefore physics and so on. So the question is, what else could you not see before that you started being able to see? And the answer, I think, is just small effects, small electrical effects, for example. How do you amplify a small electrical effect? Well, what had happened was that right at the beginning of the 1900s, there was the development of, well, things like radio and the fact that there were amplifiers, there were sort of feedback circuits that could progressively amplify a signal. And I'm pretty sure that's what was important in the development of quantum mechanics. It was also the kind of the idea of things like Geiger counters for measuring radioactivity. They were, again, these things that had sort of this notion of amplification of a small signal. And I think that's sort of the essential thing that initiated a lot of what was done in quantum mechanics. So if you look at different kinds of people, like Einstein, what was his kind of secret sauce, in a sense? I think you kind of get some sense of that from looking at his paper on special relativity in 1905. It has essentially no references, maybe even actually no references. It's a very short paper. And what it does is it argues by thought experiments. It argues about things like, if you were to have this sort of flash of light here and you were to do this and try and synchronize things and so on. It doesn't do something where it says write down an equation and then figure out the answer. It's much more of a kind of, it goes back to a much earlier tradition, in a sense, of doing natural philosophy rather than doing sort of mathematically built science. And I think what Einstein particularly brought to things was this kind of idea of let's just figure stuff out by sort of logical thinking rather than let's try to sort of have a thing that is, oh, we've got the structure, now let's build another story on this tower that we're building. So, and Einstein was a very capable, technically capable person who also sort of learned the mathematics he needed to learn in developing general relativity in 1915. He particularly needed to learn about tensor calculus, which was a pretty new thing at the time. And he always would say, it's kind of at the limit of the mathematics that I know. He wrote that in many letters and said that to many people. And I think that was, he had this sort of the logical thinking and the physical intuition to know this is what's needed. And but the actual technical stuff, he was certainly capable of learning it, but that wasn't something that was the where it came from, so to speak. I think so. In terms of how to, I think the thing that is always great to kind of identify is where are places where there is sort of a new methodological direction. That's the place where you're going to be able to make great contributions. It is much easier to make great contributions at a time when there's sort of rapid growth in a field than at a time where it's a different situation, when a field is in sort of its cruise phase, when the methodology is sort of understood for the field, and it's just a question of sort of drilling further, building further. That's a different type of contribution that can be made. I would say that one of the things that for me has been interesting in our physics project recently is we kind of hit a remarkable kind of seam of a sort of very productive, if we're thinking about it in a mining analogy, we've kind of hit pay dirt or something in I'm not sure that's quite the right terminology for mining, but we've hit this very rich seam of ideas that I have to say I didn't know were there, but this is something that has emerged from this kind of tower of ideas that that I've developed over the course of decades now. But now that we've hit this kind of seam of ideas that revolve around kind of the structure of our physics project, this idea of multi-computation, multi-way systems, all sorts of things about hypergraphs and so on. This is just a tremendously fertile kind of thing. And, you know, in the future, people will say, oh yeah, this was, you know, lots of great things were discovered around this. And in a sense, it's just, you know, this got opened up and now it's rather easy to discover great things, or it will be for a little while, maybe 5 years, maybe 10, I don't know. So that's an example of sort of a place where there's sort of discovery is in the air, so to speak. And that tends to be the places where there's a lot of clustering of sort of great things in, let's say, physics or something around those kinds of places. Now, it has to be said that, like with many kinds of opportunities, it's not the case that you can typically kind of walk into something like that and immediately solve these problems. There's usually some tower that's been built in that area, some technical thing that you have to understand to be able to get to the place where you can actually make contributions. But it's in these areas that have just been opened up, often the technical towers are, well, there's good news and bad news. The good news is the technical tower is not as tall because it just hasn't had as long to be built. The bad news is it's harder to learn it often because there aren't sort of the well-developed textbooks and courses and, you know, and exercises and so on to do because it's new and that just hasn't developed yet. So I would say that the one thing that is clear in these times is, you know, I have to give a pitch for learn computational language, you know, learn the kind of tools that we've built over these years as a way to discover things in science. If you are fluent in Wolfram language, Mathematica, whatever, you know, there are just things you can immediately do that have been completely out of reach. And that's kind of the, you know, a new thing of our times of the last few decades of the existence of that technology just makes it enables a lot of things in science and physics that were just not possible before, along with another thing that enables new things is kind of ideas, and that's a lot of what's come out that's enabled our physics project now is ideas about computation that partly come from experience with actually doing computation and understanding the tools for doing that, and partly come from pure theoretical thinking. But I would say that you're asking what sort of separates the great science crowd from the more sort of just another scientist crowd type thing. I think it's often the fact that their great contributions were at these cusps where big things were happening, usually because they brought in a new paradigm, a new kind of idea about how to deal with things. Newton did that too. Newton, you know, the title of his book, Principia, was, you know, Mathematical Principles of Natural Philosophy. Before his time, people had just tried to do the thing that I was mentioning that Einstein came back and did later, which is kind of just reason about science with philosophically, rather than having some kind of power tool to deal with it. In Newton's time, the power tool that he had was mathematics. He kind of modeled his mathematics on Euclid and kind of this geometric demonstration kind of thing, although he in fact invented the methodologies of calculus. And he was able to use that sort of power tool to build much taller tower in physics than had been built before. In today's time, that the corresponding tool is computation. And that's the thing that allows one, just as Newton was able to go in and kind of get further with physics than people had got because he had this new set of tools that were mathematical tools, some of his own invention, some that already existed. So now today, computation is that corresponding sort of new tool that exists. And I would say that computation has not been, for example, in physics, has been applied not terribly much. I mean, people certainly used Mathematica and things to do physics, but they've done physics the way physics was done before, with equations and all that kind of thing. The notion of using computation as a core idea to do physics, to actually create the structure of physics, well, that's kind of the story of our physics project. And that's, in a sense, a new story. It's a story that is enabled by all the things that we know about computation, but that's a place where one can expect sort of big new things to happen. So I think the typical thing is there's a new methodology, you learn a new methodology, you start applying it to things, even to problems where people have said, we've been wondering about this problem for 200 years and no progress was made. Well, people were bashing it with the existing methodologies. You have some new methodology, you can come in and sometimes you can just leap to the top of it and solve it with that new methodology. In fact, I'm just in the process of working on a bunch of things about mathematics and the foundations of mathematics that I'd thought about for, I don't know, 40 years or so. And they were last really worked on big time about 110, 120 years ago. And I think we can now see, using modern methods that we have and modern ideas that we have, we can kind of jump very far forward on that, on problems that have been very mysterious for a long time. And the fact that that's possible is a result of both, well, one of the things that I suppose in my particular methodology for doing things, I sort of realized this recently, is kind of an interesting methodology, which is that there's sort of two branches of the methodology. One is kind of general, sort of logical, philosophical, structural thinking of kind of how should things work, let's reason about them, and developing decent intuition for how things might work. And kind of, it's all, in a sense, just words and just things that I might talk about in a forum like this. That's branch number one of methodology. Branch number two is computer experiments and things like language design and sort of making computational the things that I'm talking about. And that's a very different kind of methodology. It's a methodology which, like the first one, forces one to have a clear understanding of what one's talking about, because if one doesn't understand what one's talking about, one doesn't have a hope of being able to explain it to a computer. But actually doing those computer experiments and so on, that's a very different kind of thing than the kind of just thinking about things type of activity. And so it's something that you're very grounded when you're doing those kinds of computer experiments. You know, you do the experiment, it does what it does. You're like a natural scientist. You're seeing, what did my computer just do? Can I understand what my computer just did? Which is a very different kind of activity than the kind of, let me just imagine something conceptually type of activity. And so it's sort of strange because, in a sense, in the things I do, there are those two extreme cases. A lot of what people do in science is somewhere in the middle. They don't think very strategically and sort of almost philosophically about the structure of what's going on, and they don't do the practical computer experiments. They're sort of somewhere in the middle, working with some level of formalism and so on. And I think the methodology that I've ended up kind of falling into using is a pretty productive one, but it's a slightly unusual one. And insofar as I've been able to discover things that hadn't been discovered before, part of it has to do with the fact that the methodology is somewhat different. So I think that's I would say, how to become a better physicist: learn computational language tools. That's a very concrete way to do it. That's one thing. The other thing is, given any question, ask, what is the real question? You're asked about, and also don't assume that some sort of slick explanation that you don't understand is the actual story. Like, one of my favorites is friction. So you may know that, people talk about friction down at, I don't know, high school level, at least physics. And, one of the features of friction is that the frictional force is proportional to the normal force. It's proportional, how hard you push the object down, the amount of frictional force increases linearly with normal force. That's the usual formula. And there's a coefficient of friction. The question is, what causes friction? And why is that law, what is that law called? It doesn't usually have it. It's named after somebody from a very long time ago, from at least the 1600s. Why does it work that way? Well, the answer is people don't really know completely. It's like, well, the surfaces have these kind of sort of rough surfaces, and the area of contact increases as you push it down harder and so on. But It's not completely clear why it should be linear. Maybe that's the first order effect and there's higher order ones, but that's an example of something where you might just say, textbook might just say F equals mu times N. That's the story, that's the end of it. Well, you can actually think about those things. Now, sometimes there will be a well understood derivation that exists and sometimes there won't be. Sometimes, like for example, in physics of, I don't know, physics of sand, that was a thing that got popular maybe 25 years ago. And I sort of wondered about it. And I kind of like, how does sand work? It's not kind of like a fluid like water where you have sort of very tiny molecules. You can actually see the grains of sand and they rub against each other and et cetera, et cetera, et cetera. And of course, that turned into a whole area of physics of granular materials and all those kinds of things. And just sort of, it's like, well, it's an obvious question to ask, but it turns out people hadn't really asked it very much. Now, could it have been addressed with methodologies that existed 100 years earlier? Probably. I think it just was a question that hadn't particularly been asked. And so I think the part of the story is, just ask the questions, even if they seem obvious. There are plenty of physical phenomena that are sort of quite everyday that people have not analyzed that well and that might be accessible to tools that exist today. I mean, I would also say that it's a general principle that the more deeply you understand stuff, the more you can really answer the sort of strategic questions about things rather than just work out the formulas, so to speak, the better chance you will have to be able to make a sort of foundational advance. Because if you're just sort of operating at the level of the formulas kind of thing, it's like, well, you'll only be able to swim at that level. If you actually understand what's down at the bedrock, you can build kind of a different tower there. Oh boy, we've got many, many questions here. Let's see. There's a question here from Georgios asking about, saying, as a physicist, didn't learn any discrete mathematics, got involved with our summer school, but didn't have enough technical knowledge to get the most out of it. What advice do I have? I think just try doing little experiments. Just the best way, discrete mathematics, for example, it's something where even much more so than continuous mathematics, you can just try that experiment, work out, I don't know, let's say, a random example. If you take random mappings, if you just take a bunch of integers and you say, I'm randomly going to pair integers up with each other, and you ask, what kind of a graph do I get when I pair up integers randomly? Well, you'll find if you try and work out what's the, how connected is that graph, those kinds of things, just do the experiments, look at them. It's trivial to do the experiments. At least in Wolfram language, it's trivial. And then say, why does it work that way? And start trying to sort of back learn the mathematics. Again, how one learns things is a somewhat personal thing. And for me, I always find it best to have a project, even if it's a fairly small one, and then try and kind of explore from the project, so to speak, what things I need to know, what foundations I need to know to be able to do things with that project. Now, our full physics project is pretty complicated, and it's probably not the place to start. I would start by looking at cellular automata, Turing machines, trying to look at the discrete mathematics of those. Those are much structurally simpler. The whole hypergraph rewriting multi-way system thing, it's just very, it's very non-human. I mean, sorry, that's just the way the universe happens to work, it seems. It's just not something we humans are particularly able to grasp quickly. Things like cellular automata are a lot easier, and that's probably a good place to start, is with experiments on those and so on. Let's see. There's a question. So many interesting questions here. All right, one from Atori. When you look at the history of technology, how far back should you go? So he says, tried to study the story of machine learning, and in some sense, the first decision tree was 500 BC and even earlier in the Bible. Yeah, well, it's always an interesting question. When did people really cotton on to some idea? When most ideas have precursors. Most But sometimes those precursors can only be identified once you have really got the idea, really wrapped your arms around the idea. Then you can go back and say, oh, these people almost got the idea. An example where universal computation, thing that arose in the 1930s, precursors in the 1920s, pseudo precursors in the 1830s. When did that idea really arise? You can start saying, well, there are these comments that are made by, I don't know, St. Augustine or something, let's say. I don't know specific ones there, which kind of sound like universal computation. But see, one of the tricky things is when you go back to a time when the description methodology was different, ideas look different. So for example, after the 1600s, after science gets mathematicized, many ideas in many areas of science, not all areas of science, get stated mathematically. And you can kind of say, oh, there's the equation F equals ma or something. We can see there's that equation, and that equation has an origin at this time, and it then moves forward. But if you say that there was a description of something that might have been force equals mass times acceleration, but it was represented as, like, say, Kepler did it as, some kind of musical score, or it was represented as some kind of allegory that was told in words and some story. Was it really F equals ma, or was it something different? By the time you have a particular description methodology, you can often say that was the origin point, because you can kind of see it looks the same as it does today. By the way, I would say that looking forwards, this is the time where the idea of computation and computational language is becoming the description language for lots of things that are discovered. And people will say, well, was there a precursor of such and such a thing? Because we can see what it's like in these computational terms now. Can we go back and see what it was like before? Now, for example, I was interested in doing that for my New Kind of Science book, trying to study sort of the distant history of things. And for example, I was interested in how were things built according to rules? Because in a sense, running a computer program is like following a certain set of rules. And so the question was, what existed in the past that was like systematically following rules? So for example, cellular automata, these arrays of black and white squares, they look a bit like mosaic. Where did mosaic originate? Well, it originated in Babylon. It was, there's a famous piece of mosaic that has some stripy pieces and some other pieces. It was, I think it's even said that it was made by Gilgamesh, although it's not even completely clear. Gilgamesh was a historical person famous for his Epic of Gilgamesh, so to speak. That was a place where, yes, the mosaic was sort of made by rules. Was it like a program? Well, not really. It was just a piece of mosaic. Then I was looking at other kinds of places where there were systems of rules. Like, for example, when you arrange in the Roman army or something, when you were arranging one of those, tortoise configurations or something, that's like lots of people arranging themselves in a particular way. Is that kind of like the rules type construction type thing? Where can you go back? Given that you now have this idea of programs, can you project backwards and kind of see that idea kind of beginning to stick its head out, so to speak, even thousands of years earlier? And it's often, if you went back and started one sort of thought experiment test is you go back and you talk to Mr. Gilgamesh when he was making his mosaic, and you start explaining programs. Would he understand, or would he just be completely confused? And it's like, I don't know what on earth you're talking about. I think that's sort of a conceivable test for whether the idea really existed at that time, or whether it needed a whole collection of intermediate kind of structure before the idea could really exist. So you mentioned things like decision trees and machine learning. I'm quite certain that there are descriptions of what amount to decision trees, if you could do this or you could do that, and if this happens, then that happens. I'm quite sure there are prescriptions in the Bible and other places that contain things which are if then type branching kind of cases. And yes, I think that's, you can think of that as the origin of a decision tree. If you ask the question, if you start asking, I mean, it depends at some level. Well, that's one which I think is as easily described in words. If you start saying, are you learning the decision tree from data? Well, you might say, well, people got used to having this decision tree because they were experienced at doing a lot of things, but that's a little different than the sort of systematic approach in modern machine learning of, systematically tweaking the weights to achieve a particular configuration. But I think it's always an interesting question when, you end up with these things, and it comes up also like, should so-and-so get the credit for idea X? And it's like, well, they almost had idea X. And if you kind of squint at it in the right way, you can kind of see it as idea X, but it's very hard to tell in many cases. I would say that even in my own life, in looking at things I've done in the past, and it's like, did I have the idea of X, Y, Z? I'll give you an example. So these multi-way systems that are a big piece of what we're doing in the physics project, when did that idea originate? Well, I mean, there are precursors to that idea, but the idea is in very much its modern form in my new kind of science book. I have a section called multi-way systems, and I've got all these pictures of these things that are what we now call multi-way systems. Now, I can talk about the precursors of that. I've tried to study the precursors. The precursors were, well, let me explain a little bit. So in a multi-way system, the idea is you have a state, like let's say it's a string of characters, and you have a rule, and the rule says from one state you can generate potentially many states. And the multi-way system, you have this whole graph of from this state you produce these states. And often from a single state you can have a branch where you produce multiple states. You can also have a merge where the states that are produced turn out to be the same, and so you merge them in this graph. Okay, so that's kind of the idea of a multi-way system. And the question is, one question is, what were the sort of precursors of that? Well, this idea that there are many possible branches on which you can go, that's an idea that originated when people talked about non-deterministic, well, first finite automata in the 1950s, then non-deterministic Turing machines around 1970. But they didn't quite have the same idea, because they had this idea of all kinds of branching, but they really said, but we want to get one answer. There is one path that is the one we're trying to pick out. There are lots of paths, but what we really want is just that one path that is going to be the winning path. So when I was looking at multi-way systems in the 1990s, I was looking at them as kind of just another kind of computational system. Didn't really think of them as particularly significant. I knew that they corresponded, you could think of them as paths through them as being like mathematical proofs and things like this, or paths through them being like chemical synthesis pathways, those kinds of things. And I thought they were an interesting idealization of those kinds of systems, but that was kind of as far as I got with them. Recently, with the physics project, this was actually partly initiated by an idea of Jonathan Gorod's about quantum mechanics, that this idea that the multi-way system is sort of a representation of the whole of reality, and that in a sense, we as observers of the system aren't just looking at the one winning path, we're actually looking at a whole cluster of paths. We're looking at this whole kind of, this will take us too far afield into the physics project to talk about this in great detail, but much like we're kind of, when we study, I don't know, molecules in a gas, we're not looking at every individual molecule, we're just looking at the overall effect of lots of molecules that determine kind of the fluid structure of the gas. So similarly, in these multi-way systems, we're not looking at a single history, we're looking at a whole clump of histories that we all sort of consider together, so to speak. And so that idea of multi-way systems where you're not just looking at one winning path, but you're looking at this whole branchial space, as we now call it, of many different paths, that's an idea that's now 2 years old. And you can perhaps find vague precursors of that idea, but that idea is kind of it's still talking about multi-way systems. It's still talking about things that look a bit like non-deterministic computation, but from a different vantage point and with a different emphasis of what's important. So that's a case where, even in, I would say, did I invent that set of ideas? back in the 1990s? Well, not really, because I wasn't really emphasizing that. Now, in fact, some technical things that I did depended on that, exactly those kinds of ideas, but I didn't really internalize this sort of full significance of this notion of things like branch Hill space and so on back at that time. So in a sense, if you say, did I have that idea? Well, you can find things where I'm sort of doing things that sort of poke at that idea, but I would say, at least internally, that I didn't have that idea at that time. The kind of the full conceptualization of that didn't come until very recently. So, this is a kind of thing where you can say, did so-and-so have the idea? Well, yes, they've got little, little sort of little points where there are sort of pieces of the idea, and you can see the idea poking through. Now, the question is, in their internal state, did they really have the idea, but they just weren't emphasizing it, or it wasn't sort of the big front and center idea? They were just seeing little pokes of the idea and so on. It's very hard to tell that. You could tell a little bit by talking to the person, but if they're no longer around, you don't get that opportunity. And you can sometimes read their writings. It's like, did they have this idea? Did they not have this idea? It's really hard to tell. I mean, I could say with some people who worked on things that are related to the physics project, there are some people, I don't know, one person who I might give a little shout out to, is a person called David Finkelstein, who I met a number of times, who was a very interesting, talented, and creative physicist who wrote a bunch of books that might relate to our physics project or might not. It's really hard to tell. And I think one thing that he even told me at one time is, he said, yes, my works are slightly confusing because sometimes I will, I'll just, if I think something wasn't right before, I'll just write a new document, but I won't even mention the older document that I now think is wrong. So there's sort of multiple archaeological levels in that case. And that's yet another sort of thing that compounds the difficulty of finding, was there something there or not? And if there was, to me, what's the value of knowing those kind of precursors? I find it very interesting. That's why I'm doing something like this Q&A about history of science and technology. I find it interesting because it helps me contextualize things that I'm thinking about now, to kind of see how the paths of thinking about things developed in the past. For example, what was obvious at the time and what was very hard to understand. A flow chart, for example, is something which is related to the decision tree thing that you mentioned, is something, flow charts seem to be pretty natural things that people invent and reinvent and so on. Whereas that's a natural thing, I don't know, what things are natural to invent, what things are not, is sometimes there are things that become natural to invent because of kind of ambient things in the world, even though they were not natural to invent when they were first invented. And some things, once you're thinking about those kinds of questions, it's natural to invent that idea. Okay. There's a question here from, there's one question here from Zayden. Is Excel a computational tool? Boy, I've never been a big Excel user. Actually, Excel has started in the last few months making use of our Wolfram language technology. You can now find a sort of Wolfram section of data entities in Excel, and I think already some other Microsoft Office products. So maybe I will, there's sort of starting to be pieces of our kind of computational language ideas and computational knowledge ideas that are poking through into Excel. I would say that in general, Excel has a bunch of interesting ideas. It's not really, it's not the kind of computational language approach that I've, for example, taken for the last many decades. Although it has to be said that in some ways, Excel is a kind of functional programming language in certain fashions. I mean, Excel, it's interesting because it's a very, okay, so in different kinds of approaches to programming, there's different levels of explicitness. In Excel, it's like you've got the spreadsheet, it's right there. what you're doing is just poking at that spreadsheet. In a language like Fortran, let's say, it's like everything is hidden away in variables. There's no obvious state of the system. It's all like, well, I set X to this and I have this array over here called Y and so on. And it's all very, very hidden. I view our kind of computational language approach of symbolic language as sort of an intermediate thing, because a symbolic expression is much more general, much richer than what you can get in just an array of numbers and so on, but it's or numbers and strings and such like. But it's something which is not the same kind of indirect hidden state that you see in something like a low-level programming language like Fortran or Java or whatever else. It's something where you can pick up that symbolic expression and you can see the whole symbolic expression. It's this tree structured thing, and it's got these different pieces, and you can kind of read them and so on. It's kind of I think it's kind of the sweet spot of being both sort of something where you can pick it up and understand it, and something which has kind of the full power of what's possible computationally. But so, I think Excel is kind of this special case of this sort of array of numbers, but it has the good feature that, yes, you can explicitly see what's going on, and perhaps even more easily than you can with the general symbolic expression. There's a question from RBS. Who invented polyominoes? Why were they invented? What role did they play in mathematics? Well, I actually know the answer to that. They were invented by a person called Solomon Golomb, who I knew fairly well for probably 40 years. He died 5 years ago now, roughly. So he was he invented polyominoes, I think, when he was a graduate student at Harvard in mathematics. And I think he did it as a kind of recreational, this was in the 1950s. He did it as kind of a sort of a recreational game. So polyominoes are things where you have a bunch of squares and they're shapes. Like if you played Tetris, it has sort of polyomino-like shapes in it. They're just a bunch of squares glued together. So you might have a polyomino that was a sort of L-shaped bunch of squares glued together, or it might be another kind of, but the idea is it's bunches of squares glued together, and those are the polyominoes, generalization of dominoes. Dominoes are like two squares, but the do part of the domino word is like it's two squares glued together. A polyomino is something where there are many squares glued together, and that word was invented by Sol Golomb in the 1950s, I think, in his original like Mathematics magazine article about the subject. He was interested in questions like, given a polyomino, can it tile the plane? So, for example, we know if you just have ordinary squares, you can obviously make a mosaic-like pattern that just covers an infinite plane. But if you have L-shaped polyominoes, it's much less obvious you can do that. Maybe the two L's can sort of fit together and make rectangles, and then you can keep tiling from those rectangles. But so he was interested in these questions about, is it possible to tile the plane with certain kinds of shapes of polyominoes and so on? Polyominoes became, there are many kind of puzzles and games and so on that developed from polyominoes. I wrote an obituary piece about Sol Golomb, and I tried to find some of the more exotic uses of polyominoes that had been made. But yeah, they were invented as kind of a sort of pseudo-recreational math idea, but then quickly turned into this question about tiling. Now, this whole question about tiling is an interesting one. Like everybody kind of knows, you can use squares to tile the plane, you can use hexagons to tile the plane. Kepler, for example, discovered some other tilings. There's the so-called Kepler tiling, which is a mixture of squares and octagons. If you just have a regular octagon, you can't tile the plane with a regular octagon. You can't tile the plane with a regular pentagon either. If you try and put a bunch of regular pentagons together, they'll curl themselves up and don't make a dodecahedron. If you make a bunch of hexagons together, they'll just make an infinite plane. In the case of so this question of what can tile the plane is one that's been interesting. As I say, Kepler did work on it. It then became something where people in the 1800s studying the structure of crystal lattices also were very interested in this. What kinds of crystals can you make? if you have a bunch of atoms that make the unit cell of a particular crystalline material, what kinds of arrangements can they be put in to still tile, in that particular case, three-dimensional space? But this question of sort of what tilings are possible was one that became of interest. And what happened, let's see, there was a question of whether it was decidable, whether something could tile the plane. What does that mean? So let's say you have a bunch of, you've got a puzzle, and it's a bunch of all identical pieces. And you're asked, is there a way of arranging those identical pieces so that you can make an infinite puzzle, cover an infinite plane with them? Now, what could happen is you could find this set of pieces and you could say, well, I can get it out to this size. I can make it a size, a 10 by 10 blob, but now I'm stuck and I can't go further. And the question is, can you prove that you can't go further? You might be, maybe you can make a size 1,000,000 blob, but then you can't go further. And so the question is, it becomes like the halting problem for Turing machines, this question of, can you, you might think it might be like that, can you determine, just given the puzzle pieces, can you say, yes, these puzzle pieces will be able to tile the plane, or no, these puzzle pieces won't be able to tile the plane? And sometimes it's completely obvious that they can't tile the plane. Sometimes it's completely obvious they can, but there's this zone of intermediate cases where one wonders, could they tile or could they not tile? So I think it was around 1960, a person called Berger showed that there was also a person called Hao Wang who was involved in this. Oh no, I'm misremembering a piece of this. There were several people involved in this. It was around 1960. This question of, was tiling decidable? That is, would it be the case that for you could write a program basically that would look at the tiles you got and would be able to say, just run a little computation and say, yep, it'll tile, or no, it won't tile. What happened, I'm trying to remember the sequence here. I think this person, Berger, was the first person who showed that there existed a set of tiles. It might be 1,000 different tiles where there was no way to know in advance whether that particular set of tiles of this type would be able to cover the infinite plane or not. What he did was he showed that if you imagine a Turing machine, simple model of computation, we already know that the halting problem for Turing machines is undecidable. That is, given the specification of a Turing machine, if we ask the question, given a particular initial configuration, will the Turing machine just keep running, always be in a loop, always be generating more complicated stuff, or will the Turing machine eventually reach some fixed state? That question is undecidable. You could have to wait an arbitrarily long time. In my way of thinking about these things, it's a computationally irreducible problem. There's no way you can kind of jump ahead and say, that Turing machine, it just wasted its time doing 1 trillion steps. I could see the answer in 5 steps. Well, that you can't do that is a statement of computational irreducibility. And then when you ask, well, what did the Turing machine do after an infinite time? Well, that you won't be able to answer with any finite computation if there is computational irreducibility. But what Berger showed was that you could map this question about tiling. You could imagine you're going to try and tile the plane. You set up a bunch of tiles as a line of tiles. And then you say, let me continue going down the page and try and fill in more tiles. And what he showed was that that process of filling in tiles was like the halting problem for a non-deterministic Turing machine. So it was, what he showed is that the question of if the thing doesn't ever halt, then that's a sign that yes, it successfully can tile the plane. If it does halt, that means it got stuck and it doesn't tile the plane. So then people tried, what he came up with was an incredibly complicated set of tiles. A person called Hao Wang, who was a fairly well-known early theoretical computer scientist, I think simplified that a bit. A person called Raphael Robinson, who I certainly met, who had been kind of a number theory person, notable as the husband of Julia Robinson. Julia Robinson, who I also met, was a mathematician in Berkeley. They were both at Berkeley. And she was particularly notable for having been a person who laid one of the important pieces of groundwork for proving the unsolvability of Hilbert's 10th problem, of proving that there's undecidability in equations involving integers. If you ask, you know, can there be integers such that x cubed plus y to the fourth equals 17 z squared or something? Can you fill in such integers that in general you can't know the answer? You can't prove that you can't do that in general with a finite proof. There might be an integer that's incredibly huge that would satisfy that, and you can't tell. It's very similar to this tiling type problem. So Julia Robinson was somebody who figured out a very clever trick, actually, in number theory, for which almost managed to completely nail the Hilbert's 10th problem thing. That was eventually nailed by a person called Yuri Matyasevich, who I've known for many years, who's at the time, that was, I think, 1968 that he finally solved that. It was one of these things where it was a time when, you know, during the Cold War, and sort of what was happening in the Soviet Union was a bit separated from what was happening elsewhere. And it was kind of this sort of mysterious moment when this young person had suddenly solved Hilbert's 10th problem, building on a bunch of work that Julia Robinson and Martin Davis and other people had done but Julia Robinson invented a particularly nice trick which almost got to the solution to Hilbert's 10th problem. Anyway, her husband, Raphael Robinson, was interested in slightly similar things, and he invented a much simpler set of tiles that would be whose general tiling question was undecidable. I have to say, I've been on the hunt for the very simplest set of tiles that have that property. I found some which got a little bit towards that in my NKS book. I'm still on a hunt for the very simplest tiles that have that property. Now, into the middle of that whole story, polyominoes are a piece of that story, and I actually don't know whether the general polyomino problem, the general polyomino tiling problem must be undecidable, but I don't. It's not actually. It's an interesting one. Maybe I should look at that one. To try and enumerate polyominoes for what the tiling sizes have to be. So into the middle of that also came Roger Penrose's non-periodic tilings. And so the idea there was, people had thought, if you can tile with something, let's say there's a particular tile or a particular pair of tiles, people had thought, well, if it's going to be able to tile the plane, then it must be possible to make it tile periodically. And it was proved a long time ago that if you have just a single tile, then if it's going to be able to tile the plane, it must tile it in a periodic pattern. There couldn't be something where, oh, you have this tile and there's a rotated version of this tile here, and there's another one there, and the pattern of how this tiling works is not something that is in periodic blocks across the plane. Now, it had been proved that with a single tile, that would be the case. If you have two different tiles of A and B, was that going to be the case or not? And what Roger Penrose did in, was that 1970-ish, I think, was to show that with a particular set of tiles, you could make something where you could show that they did tile the plane, but you could do it by basically making this kind of hierarchical structure, this kind of nested fractal type structure of these tiles. And that nested structure, yes, it could continue forever, it tiles the plane, but then you could show that there was no purely periodic structure with those tiles that would tile the plane. And so right now, there are these two tiles that Roger Penrose found in that don't tile the plane. There's actually a single tile in 3 dimensions that doesn't tile periodically, I think. Is that right? I think so. It was found more recently. But that's kind of the history of this idea of tiling. As I say, it's still an open question what the simplest sort of tiling that can happen, that can be infinite but can be non-periodic is. And actually, another interesting question is, can there be tilings where it can tile, but it's neither periodic nor nested, but a big, complicated, messy sort of Rule 30-like thing? Actually found one of those, although it's by a kind of an ugly construction that's in the NKS book, but it's not really a naturally occurring example. It's something which can tile like the Rule 30 cellular automaton, but not in a simpler way. But I've really been keen to find a simpler version of that, partly because if you do find a simpler version, you might actually be able to make crystals that were kind of repeatable crystals, but had a random structure. Let's see, maybe 1 or 2 more questions here. There's a question from Baker. Did knowing calculus allow one to make money in the 18th century or get a job? That's an interesting question. So Kepler in the early 1600s, was before calculus. Kepler had invented kind of a pre-calculus kind of idea that was relevant for figuring out the volumes of solids of revolution. Solid of revolution is you take a shape, you just turn it around in a, turn it around a circle. It's like a generalized cylinder. A cylinder is a sort of trivial solid of revolution, but you can have more complicated shapes that are sort of cylindrically symmetric, but have a more complicated form. So one particular more complicated form of relevance then was wine casks that might be, barrels that would bow out and then come back. And so Kepler had a business actually figuring out the volumes of wine casks by using sort of a pre-calculus set of ideas. And that was before calculus, probably in the, I would guess the 1610s, perhaps. I'm not sure. That's a place where somebody kind of made money from something a bit like calculus. Now, by the time we're in the 1700s, let's see, who was making money from calculus? By the 1800s, there was plenty of stuff where people were doing stress analysis of, actually, I wonder when that really took off. I was going to say analysis because there was a lot of work in building iron bridges, iron ships, things like that. And I don't know exactly what mathematics was used to figure out, yes, at those times, by the 1800s, for sure, there was a bunch of mathematical analysis of I'm not completely sure if it needed calculus or if it needed more like linear algebra to do analysis of kind of, of free body diagrams and other things where you've got these members, these beams and things that are going in different directions. I know, I'm kind of skipping around here a little bit. I know in partial differential equations that depend not only on time, but also on space, a place where those those got used a lot in everything to do with electromagnetic theory. And that was from Maxwell and people like that. It also got used the first time that I know of where kind of numerical methods for solving those were used was in World War II in the design of the wings of the Spitfire fighter plane. There was a sort of numerical calculation done with human computers that was solving differential equations there. But coming back to calculus in the 1700s, let me think about that for a second. There was, well, let's see, but by the end of the 1800s, when people were starting, for example, by the 1910s, people were solving equations that were for electric circuits and things, and those are ordinary differential equations, and even nonlinear ones like the Van der Pol oscillator equation, relevant for things like radio amplifiers and so on. So that was already pretty fancy kind of differential equation stuff by the 1910s. But let me think, going back into the 1700s, what were people doing then? Oh, yes, a very critical area. How could I forget it? Ballistics. That was a crucial early, so people, you're firing some big gun and, huge shells or something, and you fire it and it goes, it goes a mile. Well, it really matters where it's going to land, because you're trying to shoot at something, and if you get it wrong, if you get that parabola-like shape wrong, it's going to land totally the wrong place. So certainly by the time of Napoleon, 1800-ish, there was pretty sophisticated work being done on sort of ballistics tables and things, which were calculated using calculus. And I think that what you're trying to deal with there is you're solving the equations, you've got air resistance, you've got all kinds of other effects. That's definitely a calculus story. Now, I know that even in antiquity, people like Archimedes were kind of consultants on ballistics. And I assume that they were using some approximation. I don't think they knew about parabolic trajectories. I think that was a thing that must have been discovered by Galileo. who discovered the fact that the distance gone by something accelerating in a gravitational field, like the uniform gravitational field, like the one of the Earth, goes quadratically with time. That was a Galileo discovery. So I'm not quite sure what Archimedes did in terms of ballistics consulting, although I know he was at least alleged to have done that. But so ballistics, definitely one area where that would be relevant. I would think, I'm trying to think about other kinds of civil engineering with fluid pipes with fluids in them. Not sure about other kinds of things there. Let's see. Another place where people, okay, here I thought of some others. Yes, here's another one. Here's a very important one. The laying of the transatlantic cable, which was, so, you know, people wanted to run a telegraph cable initially across the Atlantic. It was very difficult to do that because you basically just had to have one piece of wire that was going to be, you know, a few thousand miles across the Atlantic. And you had to have it not break. And so it was one of these kind of venture capital-ish, you know, investment type things, you know, invest in the transatlantic cable, it will be great. Unfortunately, there's a risk that the cable might break somewhere in the middle of the Atlantic, and that happened a couple of times. But there was William Thomson, later Lord Kelvin, was sort of brought in as the consultant to the transatlantic cable company to try and figure out, was the cable going to break or not? And he was definitely using calculus to do that. And I think famously he was there with some kind of electrometer, kind of listening for the resistivity of the cable or something as the cable was being spooled out, and sort of saying you should go slower because otherwise it's going to break type thing. And he was involved in the time when the first successful transatlantic cable got laid. And I think he was made a good bounty from that. But so that's definitely a use of calculus and a place where somebody made money using calculus. Now, another one that occurs to me, and I'm not quite sure how this worked, was insurance. So let's see, for example, Charles Babbage was involved in an insurance startup. I even looked at a bunch of his account books and information about his involvement in what in those days was called a joint share company, that these days just a company with shareholders, that was involved in the insurance business. And it was, I think, so he was using actuarial tables. Was it life insurance? I don't know whether that had been invented yet. Maybe that was the time around which it was invented. I mean, the thing that's, of course, mysterious about life insurance is it's one thing to insure something where you say, well, this ship may or may not make it across the ocean, and there's some small probability that it won't make it across the ocean, but you pay an insurance premium, and if and you get paid for the ship or whatever it is in the unlikely event that something happens to it. But the thing that isn't obvious about life insurance is, unfortunately, at least in the current way things are, everybody dies. And so therefore, the chance that the insurance policy has to pay out is 100%. And so then the question is, can you sort of arrange things so that you're paying things in early enough that enough interest can be generated on that during a certain number of years that this and that can happen? And that's a pretty mathematical problem. And I'm trying to remember whether Babbage was involved in that already, or whether he was involved in more traditional insurance type questions. But and I'm not quite sure how much calculus was involved there, but certainly that was big business. The insurance business was definitely a big business at that time. Now, I mean, there's plenty of things, I don't think the people who are making steam engines, I kind of don't think they were using calculus. I think they were much more traditional inventors who were just, does it work? Does it not work? Does the thing blow up? Does it not blow up? Rather than let's solve a differential equation to see what happens. But so I think the answer is in the 1700s, I would say, I'm not immediately able to come up with a lot of examples of where you could use calculus. Well, another one, okay, the whole land surveying thing about what's the area of this field and things like that. That had been a question since Babylonian times. One of the motivators for inventing geometry actually was that question of how big is that field? How do I compare, I'm going to grow oats or something on that field. How much can I grow? Well, it depends on the area of the field. But some of the more elaborate versions of that definitely use calculus, although you can go surprisingly far without using calculus. And for example, in Babylonian times, there are sort of high school exercises, we don't know if it's high school exercises that involved these segments of circles and these lunes and this funny thing that's called the cow's nose, which is a kind of a thing made from 4 circles that's a funny shape. And it's a question, what's the area of that cow's nose shape? And in today's world, most sort of mathy experienced people would say, oh, I can just solve that with calculus. But it was solvable in Babylonian times, long before calculus existed, by just purely geometrical arguments. So I think were you to get transported back with a knowledge of calculus, what could you do? I'm not immediately coming up with the killer answer. I mean, I think there are things. I should say, in the finance area, the sort of more advanced calculus to do with stochastic processes involving some randomness that were invented, well, in around 1900, some stuff was done there, and then really, got serious in the 1970s. I'm not sure whether you could have, if wheeled back to the 1700s when there were early stock markets and things like that, could you have come in and made a killing using calculus? I'm not sure. I don't know whether the data quality was sufficient and whether there was enough kind of systematic centralized data, or whether the market was literally people coming and saying, I remember seeing the late years of the Chicago Board of Trade, you could actually see the traders, the floor traders there, a bunch of people standing completely still, and then something would happen and a bunch of people would be jumping up and waving their arms and, making hand signals that they want to buy or sell or whatever, some pork belly futures or whatever they were. But I think that the early stock markets were much more of that kind of, I'm not even sure whether anybody was systematically collecting the data on what was the price, so to speak. If there was a single trading pit where people were trading whatever they were trading in the 1700s, well, at some point, tulip bulbs in the Netherlands, that had been earlier than that. Was somebody sitting there on the side recording the price? Possibly, yes. I don't know. But so could that be handled quantitatively? I'm not sure. All right, I think we have run out of time here. And thank you for lots of interesting questions. And I look forward to continuing this another time. Actually, I'm about to do another meeting that will be live streamed. That is a technical meeting, piece of computational language design coming up in a few minutes. But thanks for all the questions here.